Recording in progress.
Oops, what is the... Good morning again, everybody. And for those who are not here, again, I just made an announcement. I hope that you guys will also follow it too, in a sense that we don't really have lab this afternoon because the lab activities, I'm planning on combining the last two labs that we have on wave optics to make it into a significant lab, basically activity. We will be doing interference and diffraction, both of them in one lab. And also, so the next lab will be actually this coming Monday. Anyway, we still have actually two chapters actually in the entire class, chapter 35 and chapter 36. Chapter 35 deals with the, both of them deal with actually the wave nature of light. And also chapter 35 deals with the interference, basically coming especially from a double slit. In a sense, you have two sources basically, and the two sources at some point they merge into a point. Now we have one wave from one source and we have another wave from another source. And when they meet, you will have constructive interference or destructive interference, depending on where they meet, okay? Somewhere in between, it's going to be some sort of an of superposition of the two waves. So that is the idea behind the interference. Diffraction, really, you have only a single slit where light goes through an opening, for example, and then all of a sudden it spreads around. And it spreads around also following behavior that is typical to waves. Historically, optics came out basically before electromagnetism. And the nature of light was a big problem. People didn't really understand what it was. What is light, in a sense, basically the fundamental question. But light exhibited at least two major phenomena, namely that when light hits a shiny surface, it reflects. And the law of reflection was well known at that time. The law also of refraction also was known. When light goes through two different media, like for example, air and water, or water and glass, or any two different media with different kind of properties, optical properties, light actually bends during the on the interface itself where the two media meet. Therefore, light, in a sense, was a subject that maybe light behaved as particles, in a sense that when you have a particle going in a stream, it hits a medium, then it bounces off. Then in this case, I would describe it as some sort of a stream of steady particles. So that was good and nice up until a point where especially the phenomenon of diffraction was a problem. Here is what the idea behind it is. If I shine light, it doesn't matter what color it is, on a surface, and if I make an opening on that surface, if the opening is big enough and the light source is basically uniform from this side, it's going to produce a shadow on the opposite side. And the shadow could be a sharp shadow, if you wish. Okay? This supports the idea of the particles going through that opening, and as they travel through, they hit, some of them are reflected, the ones that go, basically, that do not go through the opening, the ones that go through the opening are captured from the other side, and they go in straight lines. There is no problem with that. But as you make the opening smaller and smaller, then light at some point starts to diffuse. In a sense, the image is not as sharp as it was before. Around the edges, light starts to slowly but surely starts to get smaller and smaller. So in other words, the size of the image, first of all, is not the same size as the opening. The shape looks the same, but the size is not. Okay. So, and then as the size, as you move away from the center of that picture, the light starts to get less and less intense. So the intensity was a problem. As a matter of fact, if you make it smaller further, and that's what Mr. Young has shown, is that there is a clear pattern in here for where light in the middle, it's going to be bright. Then there is a place where it's going to be missing followed by place where it's going to appear again, followed by place where it's going to be missing, followed by place where its light is going to be intense again. So this succession of bright and dark, what was called fringes, was a problem. You cannot explain it with particles. It has to be a wave, and waves do that. So light at that point, we know it was something, at least in its nature, that was a wave, okay, like a sine wave. And that was in the early 1800s. That's when Mr. Young perfected his experiments with light with the double slit, where the slits are so small, but the separation between them, he controlled it, okay? If the separation is too big, then he's going to produce two basically beams at the end that are completely distinguishable from one another. If the separation is small enough, then actually they exhibit also fringes of bright light, followed by dark light, followed by bright light, and so on and so forth. That is signature of a wave, okay? That was a problem. Let me illustrate this first of all with an example. Let me get the example first from, because if we were in classroom, we would do this in classroom and we will see it, how it's going to work. So let me click on this link and let me share the link, share this link. Okay. So let me summarize basically the work of Mr. Young in this animation in here. Okay, this is the lab basically that I'm working on. First of all, I'm going to choose light in here as a source. And you can clearly see here the separation can be from 500 to 4,000 nanometers. I remind you that a nanometer is 10 to the negative 9 meters. So we're dealing with some tiny distances in here. 500 nanometers is 0.5 micrometer. Micrometer is a lot less than the hair, basically, okay? I'm gonna take a screen in here, okay? And I'm gonna shine one source of light right now. Let me make the separation a little bit bigger, because 500 nanometers for the green light is actually too much, because the green light has a frequency of around that number. I'm going to make the separation a little bigger. So right now it's about 900,000 nanometers, about twice as much as the wavelength of the green light, okay? But anyway, so I'm going to shine the light. So it's going to create as it travels, I mean, it's slowed down so much because light is supposed to travel with the speed of light, which is supposed to be super fast. But the animation here is making it so that it looks kind of traveling slow. Notice in here that this side in here is bright. That is because you have a light source, and it's bright in green because that's the light source. So I'm going to turn off this signal in here, power source. I'm going to turn on the second one, and again, it's supposed to take some time to reach the screen. And when it's collected on screen, it's no different than the first one, actually. So both of them show the same thing, that I have a source in here. But what if I have both of them going at the same time? So in here, I start to see, first of all, interference patterns forming in here, number one, in the regions in here. And all of a sudden, there are fringes in here, as I was describing, of bright green light, followed by dark green light, followed by bright green light. Now, if I increase the separation further, let's make it about 3 times the wavelength, then in this case, the separation into fringes becomes clear. Actually, there is another dark fringe that appears on the top in here, and there is another, so there are dark fringes and bright fringes. So this is what I call interference. So in this case, what's going on in here is that we have 2 light sources. The 2 light sources are supposed to have the same frequency, and so in this case, it's a monochromatic light. And in this case, they exhibit this phenomenon. If I send white light, there will be too many of them, and they will be separated. I mean, they will be kind of superposing to one another, and we wouldn't see it clearly. So let's change the color of the light. Let's make it into higher frequency. Let's send a blue light, for example, okay? So what happened in this case, remember that I had 3 bright fringes and 2, one more actually for dark fringes. Let's change quickly the frequency in here to a lot lower frequency, much longer wavelength. So this is the red light. Now the red light seems to actually spread longer, okay? But that's the same thing. It's still, you have bright fringes and dark fringes. What I mean by bright fringes is the red is intense in some points and lacking on some other points. That's basically what this phenomenon is. Again, if I increase the separation between the two sources to much longer than that, let's say, for example, 4 times as much, this is the phenomenon we're looking at in here. Then let's go to the green, because the green is right in the middle, okay, between the in the spectrum of the light, the visible light. So in this case, again, there is actually the next bright fringes is appearing in here, okay? Versus, for example, if I go back to 500 or maybe 700, you will see that I will have less of them because they form too quickly and they spread apart, okay? So the interference in here is way outside in here versus, for example, if I make it, how about 4,000? Okay, this is at least as much as you can have it in here. 4,000 nanometers is 4 micrometer. Okay, now I have a lot of bright fringes and dark fringes that are forming in here. And the interference phenomenon is very much accentuated in here. We can clearly see 1, 2, 3, 4, 5, 6, 7 bright fringes and 6 dark fringes because the outside ones are actually bright. So always there is this distinction between them. But if I turn off one of them, then in this case, the bottom light is going to be bright and there is no source coming from the top one. So at some points, I will only have a source on the bottom in here, and that's it, okay? So there is no interference in here with only one of them. So it's a kind of phenomenon that was basically fully explored by Mr. Young. In another experiments, let me show you let's look at the double slit again. So I'm going to go to the double slit experiment. So we have 2 slits again in here. So this is the experiment. So I'm going to take the slit width and make it small. Okay, this is the double slit. And the slit separation, which is this distance, I'm going to make that actually small too. And let's see, now I have only one source. And the source frequency is somewhere in between, okay? And let's show the same thing. Let's make it into a light in here again. And bring the screen again and turn on the light. So it's still a light. Okay, we want to deal with light and we want actually 2 slits. And we want the slit separation to be small, 400 nanometers, very small. And the separation between them actually to be as small as possible. Again, this is the same thing as I was talking about before. This is the same idea. So if I make the slits bigger, it actually becomes only one source in here. And as I make it smaller, back and forth. Let me go back into the single slit. This is basically the actual lab that we will be making. I'm going to make the width of the slit as small as possible in this case. And we will see that in this case, we have only one source in here. So if I increase the slit width in here, in this case, it's going to be just a big light in here in this case. So again, this is, let's bring it further away in here to see how that distance is going to show us. The formation of the waves in here in this case. Let's bring it very close in here. It doesn't show it right now, but it does show patterns of interference also in here. Anyway, so this is the idea behind the single slit and the double slit experiment. Let's see if we can change the color and if it matters. No. what I'm trying to do in here is the double slit experiment is, the single slit experiment is one of the hardest one to understand. But that is the point in here. So let's get into the theory of these things in here. So let me stop sharing the screen and understand where is this coming from? Where is this theory is coming from? So we're getting into chapter 35. So in here, what I'm assuming in here is that light is some sort of a wave. So in this chapter, what we're going to be discovering is we're going to be discovering the double slit experiment. And the double slit experiment is to prove behind the shadow of the doubt that light is a wave. As I was saying before, this thing was discovered in the early 1800s because people believed before that light was some sort of made up of tiny particles. So this one challenged that idea because now light actually, in order for it to exhibit interference behavior, it has to be a wave. Okay, so that is the whole point of this exercise. So similar to the waves that we discussed them in mechanical waves in chapter, what is it, 15. Okay, so what I'm going to draw in here is similar to the experiments I have shown in here. Control C, Control V. So think of this one as some sort of a big obviously, this is probably is not first of all symmetrical. I really need to bring this one up close up a little bit. Okay, so these points in here are basically point-like, as small as possible. So the width of each light of each opening is very small. So this is called the double slit. And from here, from this side, I have a source of one color light. So I have a source. Obviously, all of the light is going to be not passing through it. So this is called monochromatic, and the word mono means the same, and chromatic means color. Monochromatic source. So whatever it is, the wavelength is the same. It's not different from one when it emerges from this basically opening, and from this opening, both of them have the same same wavelength. Furthermore, this distance from here to here between the two slits, I'm going to call it D, the separation between the slits. The separation, as you saw in the previous basically simulation, it is sensitive to it. So how big the separation is matters. Okay, so I'm going to call this distance D. So I'm going to go very far from D, at a point way far from it, which I'm going to call this whole distance R. Okay, we're going to put a screen there, just like so. This is just a screen, just like I showed in the animation in here. And we'll try to understand how is this light is behaving. Okay, so what I'm going to do here, I'm going to take a point on the screen. First of all, there is some sort of a middle point in here. By symmetry, this point in here is the middle. Okay, so this is where the light is going to be, right in the center of the screen. Then I'm going to take two beams. I'm going to change the color in here of the beams, if you guys don't mind. So I'm going to make them blue, or make them red as to simulate. Most of the labs, by the way, we do them in red color, okay? Red lens, red. So I'm going to go to a point on the screen and call this distance R1. So this distance that is traveled from slit 1, I'm going to call it R1. So this is slit 1, and this is slit 2. Okay? So light coming from the second source would travel in a similar fashion and meet that light in the same point in here, but traveling a distance now rather than R1 traveling a distance R2. Obviously, there is a difference in distance of how much one light travels versus the second one. The difference in the path, which I'm going to call delta, is equal to R2 minus R1, as you can clearly see from this geometry. Okay, so this is the difference in path taken between the light traveling from, let's try to directly from, I'm going to call source 2 and source 1, okay, at point P. So I'm going to call this point P, okay? This is some distance from the middle axis, which I'm going to call it Y, some coordinate Y. So if I have the screen, and if it's a film, for example, and I have it exposed, it's going to develop a film. Actually, it's going to have an image. So I can go through that image and make the coordinates from the screen, from the center of the screen, up to a certain distance. That depends, of course, on how far I'm going to put the screen. Okay, so I'm going to usually make the assumption that R is very, very large compared to D. In other words, that D distance in there, which is the separation between the slits, is very small. D, remind you again, is the distance or the separation. Let's not use the word distance. It's a separation between S1 and S2. Okay, so on the source itself. Okay, so how far apart they are. Since R is very, very large compared to D, if I am very close from this point D in here, this is how it looks like from their vantage point. Near, obviously I exaggerated a lot this distance. It really should be D should be very small compared to R, okay? Even when we do it in the lab, you will see that the sources are very close from one another, and the distance is several centimeters, I mean about 20, 30 centimeters away. And the others is very, very small, okay? So usually we don't, this image in here is exaggerated just to show you the separation of the two, okay? They are very close from one another. That's exactly what Mr. Young, so this is Young's experiment. Okay, so let's go very near the slits. So this is how it looks like near the slits. So I have an opening in here. And next to it, there is another opening. So this distance is, so this is how it looks like. One beam leaves from this side and goes toward infinity, where R is, okay? And the other beam leaves the second one and also goes very far away, where the two meets at infinity. So the two lines will meet at infinity as far as the two slits are concerned. The two beams of light meet at infinity as far as these two slits are concerned, because remember R is very, very big compared to D. So this distance is D. So we're looking at a very tiny region of the slits. By definition, two parallel lines, they don't meet, or if you wish, they meet infinity, which means they don't meet, okay? Two parallel lines meet at infinity, meaning they don't meet because infinity doesn't, I mean, it's very far away, basically. So this lines immediately in the neighborhood of these two is actually, they're parallel to one another. So if I draw the orthogonal to both of them in here, this line, This is the distance between them, because as far as this is distance from this point on and this point on, they're equal because they're going to meet at point P, which is very far away. But this is the only one, the only difference between the two. This is this is how far the other one travels. The second one travels compared to the first one. So this is actually what I meant by delta, which is the difference between the first two as they meet. So this is actually equal to R2 minus R1. So this is the difference in travel, because from this point on, when they after the orthogonal, they will be traveling in the same distance and they will meet somewhere at infinity. Okay, so this is an approximation, and the approximation relies on this R much bigger than D. Okay, so let's look at the geometry again. I'm going to call the following angle. Let me draw it green. From this point, from the middle to here, and this distance, first of all, I'm going to call it R, okay? So this is the R, if you wish. And it's also immediately in the neighborhood is parallel to both of them, because in the neighborhood, it's here is that line. So it's from the middle, actually, and it's parallel to them, and it's going to meet them also in the same point P. So all of these three lines are actually the same thing. They are actually parallel to one another immediately, but after a while, after a very long distance, they start to converge to the point P. So this angle in here, I'm going to call it the angle theta. Let me draw that angle. Again, this is the middle, and this is the middle that is going to go to the middle of the screen. This is the angle theta, by definition. Okay? So this is the angle that I can clearly see from this geometry, whose tangent is equal to, this is the theta again. This is the angle theta whose tangent is equal to y over r. So tangent of theta from the geometry is y over r. Granted that r is very big compared to d, but it doesn't mean that it's, I mean, y has to be small enough in order for this whole thing to work. Okay, so this is the tangent. It's the opposite over the adjacent in this right angle triangle, and this geometry also. Okay. So it's all a matter of geometry at this point. So this is the same angle theta that is equal to that arc tangent. Look at these two angles in here. This side of this angle and this side of this angle are perpendicular to one another, because remember, this is perpendicular that I chose by definition in here, and this line are perpendicular. Therefore, I mean, they're parallel. Therefore, this is also perpendicular. This is a 90-degree angle. So this side and this side of theta and this side of this angle are perpendicular. Furthermore, this side and this side of the other angle also are perpendicular, because that is actually by symmetry too. They have to be perpendicular. Therefore, this angle also must be theta too. In other words, this angle, which is theta, is the complement of this angle in because of this right angle triangle. So this plus theta is equal to 0, and this plus this angle, I mean, equal to 90 degrees, I'm sorry. And this plus this angle is also 90 degrees. So this and this must be the same angle theta. So the geometry clearly states now that this angle also is theta. From this geometry, you can clearly see that sine of theta. Let me redraw this triangle again carefully, okay? Because I was not. Let me see if I can get some of the stuff in here deleted, because it looks like it's not a straight line, and it is not, because I was trying to draw it by hand. Okay, so this is the triangle that I'm talking about in here, which is this. Between the center of this slit and the other one. Okay. Remember, the slits don't matter because their size, because at this point their size is very, very negligible, very small compared to everything else. So this is the right angle triangle. So let me redraw that right angle triangle again. So this is how it looks like. So this is the separation D between the slits, and this is the angle theta. This is theta. And this is delta. you can clearly, and this is perpendicular. I chose it to be perpendicular by design, actually. So this, in this right angle triangle, the sine of theta is equal to the opposites over the hypotenuse. So the sine of theta, again, is equal to the opposite, which is in this case delta over d. Okay, so we have quite a few things already from the geometry. We have tangent theta, the same theta is equal to y over r, but we also have this sine of theta is equal to delta over d. So I'm going to make this two waves, okay? Again, at this point in the early 1800s, we really didn't know what it was waving. But in light of physics 2, which is chapter 32, actually we know exactly what is waving. We know that it's the electric field and the magnetic field that was discovered later on by Mr. Maxwell, basically to be the solution to Maxwell's equations in vacuum. Therefore, actually, the symbol in here, I'm going to use it, although we could use any symbol for this wave, but we're going to use the symbol E, referring to somehow the electric field. So the electric field, or the light in here that is expressed in here with this wave, is going to be represented by some wave of cosine of kx, or kr, I should say, minus omega t, where k is the wave number related to the wavelength of this thing that is waving, whatever it is. And omega is related to the frequency of whatever is waving. So that is basically the basic equation for waves. So this is waves, okay? So this is coming from source 1. This is coming from here. So this is E1. E2 is going to be identical to the first one, except that there is a shift in distance by the amount delta. When they meet at point P, by the way, when they meet at point P, the omega t doesn't matter because they will meet in the same instant, but there is only one of them traveled longer than the other, that's all. So this factor could be omitted from the analysis altogether because it's not going to impact what's happening in terms of the intensity of the wave at point P. But we're going to keep it if you want to, okay? Because in order for interference to happen, the two waves must meet in the same point P at the same instant. So this is waves in general. Since we don't know what it's waving, we can write it any symbol we like. But again, in light of what we know from chapter 32, this is actually the electric field and the magnetic field. So we're going to take one of them, the electric field, to be representative of this wave. Okay. And what I'm saying in here, it has an intensity E naught. So this is the intensity of the wave. Okay. Times the cosine of this k times the displacement minus omega t, where r is actually that r1. So this is exactly r1 actually, okay? It traveled the distance r1 to get to that point P. E2 will be in a similar fashion coming from the second source as equal to E naught times the cosine of k r2 minus omega t, where t is the instant when the two waves meet. The only difference between them is one traveled the whole distance r1, whereas the other one traveled the whole distance r2. And these two different distances are not the same. They're actually some sort of a one of them traveled longer than the other. Obviously, if I'm looking at the central point, if p is equal to 0, the origin, both of them will travel the same distance by symmetry. So in this case, r1 is equal to r2. But I'm taking the most general case. I'm taking a point P on the screen that is not necessarily in the center. So any point on the screen in here would do. If you want to, you can put y equal to 0, and you should recover the central fringe. Okay. So let's continue now and see what happened when the two waves meet at the point P. Well, the superposition principle that we use in waves state that the following, that the wave equation, if one wave is a solution and the second wave is a solution, the sum of the two is actually a solution. And that's exactly what interference is. So E at point P, at P, would be simply E1 plus E2, the sum of the two waves. So it's going to be, and E naught is the same because both of them are coming from some sort of a source that has the same intensity, and the only these two things have to do is just split that. So E naught must be the same intensity. So whatever controls the intensity controls it for both of them. So E naught is the same. As a matter of fact, it's not E naught only. E naught and lambda and F are all the same because it's a monochromatic light coming from the same source. So are the same because the light is monochromatic from the same source. And the same source means something very, very important, because if the source is sitting in the middle in here and spewing waves at a constant rate in here, which is F, the frequency, and this traveling at the rate of basically how far the wavefronts are separated by the same wavelength lambda. So when they hit this one in here, they will have the same intensity at this point and this point by the symmetry. So E naught is the same for both of them. And lambda that is going to emerge from here and lambda that is going to emerge from here is the same because it's coming from the same source. And F that is coming from this point and F that is coming from that point is the same. That's why I did not change anything in these expressions between the two sources, other than the fact that one of them traveled longer than the other, that's all. Okay, that's the only controlling factor, is that R1 and R2 being different. And they're being different because I'm sitting somewhere on the screen, so that this, from the geometry, clearly that R1 and R2 are not necessarily the same. So now it's a matter just of playing with these things in here. So let's sum this stuff and see what's going on. So I'm going to use some trig identities. So E is equal to E naught, open parentheses, cos of KR1 minus omega t plus cos of KR2 minus omega t. Actually, for convenience, I'm going to write R2 first and R1 first. It doesn't matter. The cosine is in a even function, so even if I find it the way that I don't like to find it, I'm going to flip the signs and it's going to be the same thing. This is simple because this is just commuting the sum in the of two numbers. So I'm going to use this identity if you guys. I'm going to say cos of alpha plus cos of beta, and cos of beta, not beta, and see what that is equal to. Okay. So there is an identity that says that this is 2 times cos of, let me try to remember it, okay? Or prove it, okay? Because if you can't remember something, you can prove it. And it's actually a good exercise to show that. What I'm going to say in here, I'm going to say cos of A plus B first, okay? Is equal to cos, because that's an identity that I remember. In other words, you don't have to remember everything in here when you're doing stuff like this one. Is minus, what is it? Cos minus sine of A, sine of B. This identity I know, so this is an identity. And also, cos of A minus B is also cos A, cos B, plus sine of A, sine of B. If I sum this two side by side, this cancels, and I will end up with 2 times cos of A, cos of B is equal to cos A plus B plus cos A minus B. Okay, good. Now, I'm going to call A plus B as alpha. And I'm going to call A minus B as alpha, as beta. Okay, if I do that, it's clearly from these two equations that A, when I add this side by side, I will get 2A is equal to alpha plus beta. So A is just alpha plus beta divided by 2. And if I subtract them side by side, B minus B, that's actually going to be 2B. Of course, the A cancel. And I will have alpha minus beta divided by 2. So in other words, I found what the identity I needed from two well-known identities, from this two, which is actually the same identity. So there's just a sign in here changed, that's all. So cos of alpha plus beta, plus cos of beta, sorry, is simply equal to 2 times cos of the sum divided by 2, which is alpha plus beta divided by 2, cos of the difference divided by 2. Here is why I was kind of didn't like that order in here, because I know that I will have the difference between these two arguments. Obviously, in the difference, omega t and omega t cancels, because minus omega t minus omega t will cancel. But I will have, if I left it the way it was, I will have what looks like it's R1 minus R2. But because the cos is an even function, that would not have mattered, because I would have R2 minus R1 in the cos, the same thing as R1 minus R2. So that's why I was kind of not hoping to write it that way. This one doesn't matter, because this one is just the sum divided by 2. So it's going to involve k times R1 plus R2 divided by 2 minus omega t minus omega t, which is 2 times omega t divided by 2. So it's going to be just minus omega t. So again, we're ready now to write this expression in light of this identity now, which is derived from a well-known identity from trig functions. So now the intensity E at point P, so I'm going to label it with a point P now. Okay, this is the intensity, I mean the wave at point P, that is coming from the summation from the superposition of the two waves, by superposition actually, of the two waves coming from the two sources S1 and S2. Is going to have a 2 first of all, this 2. Cosine, I'm going to write this term first. And let me tell you why. Because the omega t drops from it. So I took it in the most general case just to show the case, there's the point that this does not depend on t, because I will have this argument minus this argument divided by 2. And this argument has minus omega t minus omega t, so it's going to be canceling. So the only thing that's going to be left is k times R2 minus R1, which is delta, divided by 2. So it's going to have a k delta divided by 2 times the cosine of the sum of k times R2 plus R1 divided by 2 minus omega t. So this is coming from the sum. But this term is irrelevant. This is a wave. So the sum of two waves is a wave. That's what this term is. Okay, it's the times E naught. I'm sorry, forgot the E naught in here, because we had an E naught multiplying everything in here. Here at the E naught. But the intensity of this wave is the one that is, the intensity of this one is the one that depends on delta. K is constant, depends on delta. And delta, if you guys remember, depends on where we are looking for this wave, because delta is equal to actually d times sine theta from this expression. And it's equal to theta is related to where the point is. So this intensity, actually, this is the wave, not the intensity, because the wave depends on delta, which depends on theta, which depends on y. In other words, there are places where this thing can be 0. There are places where this thing can be actually equal to 1, and so on and so forth. The wave, and this is actually coming straight out of chapter 32, okay? The intensity of the wave and actually it's not coming just from, it's even from chapter 17, chapter 15, because waves always are proportional to the square of the amplitude. And the amplitude initially was E naught, but now the amplitude is this whole quantity. So the intensity depends of the wave is proportional, and I'm not saying it's equal. I'm saying it's proportional to 2 times E naught times the cosine of K delta divided by 2 squared. That is the amplitude at point P. Okay. Now, if I'm not looking at it that way, if I take one of the slits and cover it, okay, with screen like I did in the demo, then in this case only E naught will come out and will be at point P E naught. So in this case, the intensity will be E naught squared. But now it's not E naught squared. It's 4 times E naught squared times cosine squared cosine K delta over 2. Okay. So that is what makes this thing different. Okay. So in other words, I naught is proportional to E naught squared. I in the point P now is proportional, not equal, is proportional to 4 E naught squared times cosine squared of K delta over 2. The only difference between them, so if there is a factor of 1/2 of mu naught or epsilon naught and whatever you like, speed of light in here, there is the same factor in here too. And if I take the ratio of the two, those commonalities will cancel, including E naught squared also will cancel. And then at the end, I at the point P will be simply whatever I naught you start with in the beginning times 4 times cosine squared of K delta over 2. This is the intensity of the wave at that point. This is a very important result. Okay. And it is important in here to know that this expression, all it does is gives me the ratio of the intensity at point P coming from 2 sources versus that coming of a single source, okay, in the same point. And that is equal, the ratio is equal to 4 times cosine squared of K delta over 2, okay? This cosine squared could be 0, it could be 1, which means that I could get into the dark fringes and bright fringes as I was talking in the introduction, okay? So what matters, what controls this factor is this one, and the factor 4 too, which is unique to interference. This one came from the sum of the 2 waves. So in other words, if I take a particle and throw it to the wall and send another particle, I will have 2 particles. But if I have a beam coming out with an intensity E naught, and I have a beam coming with an intensity E naught, I naught, I'm sorry, intensity I naught and an intensity I naught, and put them together. At some point, I will get 4 times as much I naught. And some places I will get 0, because this cosine squared theta can be 0. Cosine squared K delta will be 1, positive 1, because it's always positive, if K delta over 2 is exactly a multiple of pi. Because if it's 0, it's 1. If it's pi, it's -1, but you square it, it's going to be 1. If it is 2 pi, it's going to be again positive 1. If it is 3 pi, it's going to be -1. When you square it, it's going to be positive 1. So this one is a multiples of n pi, which I'm going to write it m pi, where m can be any number, positive or negative, 0, positive or -1, positive or -2, whatever you like. Okay. So this, I have constructive interference in that point. Interference in P, meaning P is a bright fringe. So if it was red, it's going to be super bright red, brighter than even the one with only a single slit open. If you cover one of them, it's going to be bright. But when both of them are open, that point actually is going to be super bright. 4 times as much as you started with. Okay. Obviously, I need to solve this equation. I have K delta. Let me go back into the deltas that I found in here involving this expression. Remember, delta is d sine theta. And K is just 2 pi over lambda. So let's put everything together now. So what we have in here, we have 2 pi over lambda times, that is your K, times delta. and delta, which is just d sine theta from this expression, from this geometrical argument that I made before. Delta is just d sine theta from this triangle. And then I have a factor of 2. Do not forget this 2 in the denominator. So divided by 2 is equal to m pi, where m is anything you like as long as it's an integer, positive or negative. So all of this are bright fringes. Obviously, I have some cancellation. The 2 cancels the 2, the pi cancels the pi, and this expression is used written this way: d sine theta is equal to m lambda. So this is the condition on bright fringes. If you want to find them on the screen, use the second relationship to find them. R tangent theta is y over r. So you can find y as being r tangent theta. So the y on the fringes in this case is simply equal to r times tangent of theta. Okay, so this is where they are on the screen, location on screen. So we were able to find the bright fringes. Now there is an approximation that we're going to use. Okay, theta is in radians. Okay, so if we were doing this lab and I had this major problem in one of my classes, okay, theta has to be in radians. Then of course, if I use the Taylor expansion, sine theta will be approximately equal to theta minus theta cubed over 3 factorial plus theta to the power 5 over 5 factorial and so on and so forth. Cosine theta will be simply equal to 1 minus theta squared over 2 factorial plus theta to the power 4 over 4 factorial and so on and so forth. I'm going to neglect anything of the order higher than theta squared. So that means for small thetas, theta in radians, okay, sine of theta will be approximately equal to theta plus 0 of any order higher than theta squared, okay? Cosine theta will be the same thing. Actually, theta cubed, if you like, okay? Because cosine theta in the same order is going to be roughly 1 minus theta squared over 2 factorial, which is 2, plus anything order than theta cubed is 0, okay? So if you do that, the tangent theta, no, let's neglect anything of the higher order theta squared, okay? I don't like that too. So tangent theta will be simply equal to sine theta, which is theta over 1, which is the same thing as theta, which is the same thing as sine of theta, okay? So sine theta and tangent theta in small angles, as long as they are in radians, are the same as theta. In general, sine theta and tangent theta are the same, regardless in radians or degrees, if theta is small, okay? Small enough, like 20 degrees, 17 degrees, 18 degrees, a lot of the time, even 27 degrees is small. And you test it on your calculator and you will see that indeed the sine and the cos and the sine and the tangent are very close from one another. So in this case, sine theta and tangent theta will be very close from one another. So I'm going to take the ratio of the two. Obviously, in this case, y will be equal to r times tangent theta, which is roughly sine of theta. And sine of theta from the geometry is equal to exactly m lambda over d. So this is r m lambda over d. So from here, I can find the position of the maxima or the bright points, okay? They're given by m, which is an integer, times r lambda over d. Meaning, if m is positive, first of all, for m equals to 0, that's a bright fringe. This point is bright. Okay, if I move away from this, take a positive 1 or negative 1, I'm going to find the next bright fringe in here somewhere on the screen. So this is for positive, it's going to be bright. For negative, it's going to be bright in here, and so on and so forth. For bright in here, probably this is bright. And then there is another one in here, bright, and so on and so forth. Obviously, I didn't say anything about the dark fringes. Well, the dark fringes, they form in this case when this cosine is equal to 0. If that cosine is equal to 0, then it doesn't matter. When you square it, is going to be 0. So the intensity at point P will be actually equal to 0. So if cosine squared of k delta over 2 is equal to 0, this is a dark fringe. So that means that k delta over 2 must be either pi over 2 or 3 pi over 2 or negative pi over 2 or negative pi plus pi over 2, which is negative 3 pi over 2 basically as multiple. So here is how we write it actually. We write it as m plus 1 half times pi, okay? Where m can be anything you like, 0 again, or plus or minus 1, or plus or minus 2, or anything like that. Because if it's plus 1, I will have 3/2 of a pi, which is 270 degrees. Or if it's negative 1, actually it's going to be negative 1 plus 1/2, which is negative 90 degrees, and so on and so forth. All of this will make the cosine 0, okay? And k delta satisfies that condition. So again, we're going to replace k by 2 pi over lambda times delta. Delta is just basically from that expression, which is d sine theta, over 2, don't forget the 2, is equal to m plus 1/2 times pi. Cancel the pi from both sides, cancel the 2 from this side. And now the condition for the dark fringes is equal to d sine theta is equal to m plus 1/2 times lambda. So this is dark fringes or destructive interference. In other words, if I choose the point P in such a way, I am this distance in here. What is the? Then this is dark. There is no light in here at all. And this is the dark, and so is this one. And by symmetry, there is always one on top of the other. So they always come in pairs, actually. Okay. The central one is going to always be bright, and then the next ones, they come in pairs, okay? The dark fringes are always going to be coming in pairs, no matter what. So if you have 2 in here, you have 4 in here, you have 6, and so on and so forth, okay? Here is the location for that also, similar to my argument earlier for the location of the bright fringe, using the same expression. Y min now, if I'm looking for them, Y min, again, is equal to r times tangent of theta. I'm going to use the same approximation where tangent theta is just given by sine of theta. And sine of theta from this expression is just this whole thing divided by r. So it's going to be divided by d, I'm sorry. So the y min is going to be equal to r times lambda divided by d times m plus 1/2. Okay, so this is their location again in here. So take r lambda divided by d, multiply it by 1/2, and you will find the first one. Make m equals to -1, it's going to be -1/2 times r lambda over d. Whereas the first ones in here, they're going to be just exactly either m equals to 0, which is a central fringe, r lambda over d, or the next one, which is r lambda over d times 1. So the first one in here is just 1/2. So in other words, here are the locations of the screen. The central one is going to be bright, so this is bright. If you go r lambda over d in the y-axis, so this is actually distance. So this is r lambda over d times 2 in the denominator in here. This is actually dark. If you go twice as much, which is r lambda over d, this is actually bright. And you guessed what's going to come next is going to be r times 3. So it's going to be 3r lambda over 2d. That is going to be dark, actually. And if you go twice as much as this one, which is 2r lambda over d, that is going to be bright. And the same picture is happening below on the screen. Okay. So we have found actually an interpretation of this phenomenon if and only if light is a wave. If light is a wave, then we are in business, and we can understand everything in here that has to do with this thing in here. So this is our interpretation for it. And as I said, before this chapter, namely chapter 35, is happening after chapter 32, because in chapter 32 we discover actually it's the electric field and magnetic fields that are waving. Historically, though, the wave was discovered later, in a sense that we knew it was waving, so that's why when Mr. Young actually was using the symbols, and everybody around his time, they were using for the wave chi, okay, because they didn't know what it was waving. So they were using this symbol, and the argument would work the same, because this one doesn't care what was waving. What cares about as long as you can find a wave. Now you can find lambda, because all of these experiments, and that's part of the experiment that we'll be doing, is you can find lambda, because if you can go and find where the dark fringe is, or the bright fringe, it doesn't matter. If you take a ruler, okay, a ruler, and measure this distance from here to here on the screen, this should be, according to this one, from the central bright fringe to the central bright fringe, should be r lambda over d, provided that lambda r is very, very far away compared to d. That's fine. So you know how much that distance is. That is actually the distance between the fringes. So I'm going to call it y max. Okay. As a matter of fact, usually in the lab we calculate this whole distance from this top to the bottom. Okay, which is going to be just twice this number. That's all. Okay. So if I assume that I can measure this distance with a ruler, and I'm careful with it, so I know what that distance. From here, I can find exactly what lambda is. Lambda is simply that measured value times d, which is how far apart the two slits are, which I can control by construction. So d, I know what it is. And r, I know where my screen is located. So if I can measure all of these distances, I'm in business. I know exactly what I have found. I have found the wavelength, although I had no idea what was waving in the time of the early 1800s, but I know the wavelength of that green light, for example, versus the red light, versus the blue light. So we know there are different wavelengths. Now, if we know, and there was actually experiments at that time that tells us, and we know what the speed of light is, c, and if light is a wave, it better obey a wave dispersion relationship, where the wave c is equal to lambda f. So if I can measure c, which was measured independently, use this experiment to measure lambda, then I know what the frequency is. So not only I know its wavelength, I know its frequency also. And we had no idea what was waving in the early 1800s. We know light was a wave. That was a big deal. That was a big deal. Obviously, it was a mystery. One of the mysteries is, here is the thing. If you take the string, and you disturb the string. So let's fix the string from one end in here. And somebody creates disturbance in it. So this string will have a wave traveling in it. So we know what's going on in here. It's a mechanical make. So basically the parts of the string, the wave in this case is moving in the string. So this is waves moving in a string. We know that. If you go to the surface of the water, and you create a disturbance in the water, you know that the waves that form will travel over the water surface. So there is a medium required. As a matter of fact, in here, if you guys remember, the speed of the wave was related immediately to the tension in the string, which was a force divided by the linear mass of the string, okay? So this is the wave of the spring. This is from chapter 15, from a long time ago, okay? So the properties of this wave in here, it needs to travel in a medium whose frequency, whose force tension in it is F, and mu is basically the characteristic, how much inertia it has. So this is the inertia of the medium really in the denominator. This phenomenon is also true for the speed of sound too in vacuum, in air. Sound does not travel in vacuum. It needs air also for it to travel. And that has to do with the Young models. The speed of light, the speed of sound was 343 meters per second in normal air at room temperature. And that required a very, very strong Young models, basically structure. The speed of light, though, was known to be around 300 million meters per second. So think of this one. It's about 1 million times more faster. 1 million times faster than the speed of sound. So the medium with which light must travel then must be super, super dense, extremely dense. This suggests, this analysis about the waves, that the medium has properties that it is super dense. Yet, it has to allow for light to travel through long distances so that we can see it. Because, case in point, light comes from the sun to here, travels a distance of 150 million kilometers, travels actually much more longer distances to come from other stars. So this medium has some weird properties, okay? Super dense medium with weird properties in terms of its optical properties. They gave it a name. We're talking about the early 1800s, okay? Because of what's coming out from this. They gave this name the ether, okay? So this medium must exist because there is no wave that we know of other than light that requires medium. All waves require medium. Sound requires air at least, or another material. Water waves require water. Seismic waves require earth. String waves require that. Slinky, for example, requires this thing in here to work on it. So we know waves have that medium requirement. So now we know it's a wave because we can find its wavelength. That is what this whole experiment was saying. Not only that, we can find its frequency also, what this experiment is suggesting. And we know its speed too. So we have a dispersion law. So this is the dispersion law that it must obey. Furthermore, Mr. Maxwell came up with equations that actually confirmed this equation in here and showed that actually what was waving, we know what was waving. It was the electric field and the magnetic field. So it was the electric field plus the magnetic field together as both sides of one side, what was waving. We know that. So now Mr. Michelson and Morley decided to come up with an experiment to see how fast the Earth is moving around the ether, because the ether must exist. Otherwise, we have a problem here. So this is the experiment that they have designed. They designed an interferometer, basically. So you have a light source in here. A light source travels, comes through a semi-transparent mirror. Part of the wave goes through, 50% if you like, and goes through a reflector. In other words, it's going to bounce back. Okay? And the other part of the wave is actually transmitted at a 90-degree angle. I cannot draw verticals. That's why you guys saw me with this thing in here. So I'm going to draw it with this line in here. So part of the wave is going to be going at a 90-degree angle and goes through another reflector. Okay, so the outgoing wave must bounce back again when it comes back. So it's going to come back in here. I draw them far away, but they are not really meant to be far away. They are supposed to be at the same point because, again, these are reflected waves. Okay? So this comes back in here. Now they go through the reflector again. So the first one that comes from the bottom is going to be reflected to the bottom. So in here. And the one that came from straight out is going to come straight out in here. Oops. So let's just Control-C it and Control-V it and put it next to its sister in here. And in here, I have an eyepiece in here. So here I have a detector. Okay, here is the deal. I take my apparatus and point it in one direction in space. It doesn't matter. I know the Earth is going around the sun. Of course, this is on a table, okay, not on. So this is a semi-transparent, not a fully transparent, not a. So it has this property of sending waves. Now, if the Earth is traveling in this direction with respect to the ether, so this is the velocity of the Earth with respect to the ether, then light going here in this direction travels a longer distance because this whole thing is shifted in this direction, while with the Earth, versus this one that goes straight up but perpendicular to the direction of travel. So this will travel less. So because of that, although I have only one source of light in here, there is a shift. One of them is going to travel longer than the other, and I should see interference in here. How much interference I should see? Depends on this V with respect to the ether. So this is the V Earth with respect to the ether. How fast the Earth is moving with respect to the ether. Well, if you say, okay, no, actually the Earth was going at this angle. Okay, that's fine. Then this must travel longer than the other one. And in this case, there will be interference still, because one of them traveled more than the other. There is one of them that has a longer optical path than the other, because the waves are more chromatic to begin with. They are of the same source, so they have the same omega, the same f, the same everything in here. All of the things are they're the same. And the only thing that is different in here is one of them travels longer than the other because it's shifted in space because of the motion of the Earth. Okay. So the minute that it hits in here, the Earth would have moved for it to come back and so on and so forth. So there is a delay for this one, okay? Because in this motion, or the other one, if you like, okay? When they first conducted their experiment, so this is a Michelson-Morley. I think Morley was a student of Michelson. This is in the late 1800s. They found that V to be zero, this velocity to be exactly zero. So they didn't abandon their product, and they said, okay, we really were lucky. This is the day when the Earth was apparently stationary with respect to the ether, because the velocity was zero. If we wait 6 months from today, here's the deal. Here is the Earth now. Here's the sun, I'm sorry. Here's the sun. Here is where the Earth is. And if this is the day somehow where the Earth is moving around the sun this way, and in the same time it's moving around the ether this way, so the two velocities probably they cancel. Maybe there is another effect or something, so that the relative Earth motion of the Earth with respect to this experiment is zero. In other words, we're getting zero because the Earth is actually moving around another coordinate system. So today is actually where the velocity is zero. If we wait 6 months from today, the Earth actually will be on the opposite side of the sun, and the Earth should be moving in the same direction with the ether. Then we will find basically what the velocity of the Earth will be with respect to the ether if we cancel out that motion with respect to the sun, and that's fine. We should be able to find it. Okay. After 6 months, they found nothing either. This experiment was refined further and further and further and further and further, and they still found nothing. Took the genius of Einstein to look back into the equations of Maxwell and saw that those equations, they work in vacuum. There is absolutely no need for the ether at all. And this is a special case of a wave that does not require a medium at all to travel. So ether hypothesis was abandoned because of this experiments, and ether was not needed as a hypothesis for this one. So this wave's light travels in vacuum. Does not really require medium for it to travel. So this is in a nutshell, basically, with the whole story toward the end. They have 2 C's in here. I know there is one of two things, okay? Does not require a medium for it to travel. So light travels in vacuum still. So all of the other waves are one thing. But when it comes to this type of waves, that does not require a medium. So what do we take from this? And I know we have another session coming down the road on Wednesday, okay? For those who came out late, the lab is not, there is no lab today. The lab, because I'm combining the two labs, the last two labs together, and we're gonna have a nice combined big lab coming Monday next week, okay? So this is, we're gonna meet on Wednesday to discuss the problems from this session. And then we're going to ready ourselves for chapter 36, which is gonna be the last chapter of this class. And one big lab that is coming this coming Monday, okay? So, so we're going to have applications of this one. So what do we take from this one? The main points from this, I mean, in other words, how to do problems. This relationship, how to find bright fringes. It's very important, okay? How to find it. Dark fringes, how to find them. So it's similar to the first one, except in here I have an odd number of 1/2, basically, of wavelength. And I mean, if you want the argument, and I know there is a couple more points that probably I need to touch upon for this one in here. Here is the deal with the first one. So if there is one wave, difference between the first one and the second one. In other words, the first one comes in, and the second one, for example, travels a whole wavelength more, or multiples of that. There is a match then between the top of this wave and the top of the other wave, and you have constructive interference. If one of them travels half wavelength or an odd number of half wavelengths, then the first wave and the second wave, when they meet, they cancel. So you have a cancellation. In here, you have an overlap between the two. So when you add the first and the second, it's going to be twice as much, because point by point is going to be twice as much. And since the intensity is proportional to the square, so since it's twice as much, when you square it, it's going to be 4 times as much in terms of intensity. So the amplitude will be twice as much. And when you square it, it's going to be 4 times as much. And here, they cancel out. So that's why half integer wavelength was giving me dark fringes, because one of them is coming on top, the other one is coming on the bottom. When they do, they cancel. Half wavelength or any odd number of half wavelengths, they will always have the same effect, okay? Because this one is here, the other one is here, the other one is there, and so on and so forth. So this pattern is changing, either 1 or 3 of them, or 5 of them. And in the first case, you have a full wavelength and a full wavelength, so the new wave is actually twice as much in terms of amplitude. When you square it, it's going to be 4 times as much. So this is the essence, basically, the geometrical interpretation of what's going on. There is another point in here that I didn't talk about, and that is what happened when you have waves hitting a medium. Like, for example, when there is an oil spill during a rainy day. So what you have in here in this case is that you have waves coming to the surface, and the waves that are reflected, in this case, you have one wave that is reflected from the top surface, but there is a wave that is going to continue in here, and that's going to come out from the second surface in here. Depending on the thickness in here, T, of this spill, if you wish, or actually take a CD-ROM and put it in front of the light. Depending on the angle, also you'll see all kinds of colors. That's why you see all kinds of colors in here, because there is all kinds of interference. So you have a white light now that's coming, and the white light starts to separate. Some of them are missing, some of them are brighter. So in this case, the ones that are missing will disappear, and the white color now gains. I mean, the white color becomes colorful. In a sense, you will have some colors. For example, the red is missing. Now you have the combination of the green and the blue. Okay, I would give you that. What is that? Violety color. Okay. Or, for example, you have the red and the green combined, because the blue is all of a sudden missing from the color, and now that is yellow. So you have all kinds of colors that form in this case because of the combination of what is missing and what are missing actually versus what is present. So you'll have the different, and here depending on the T, and depending where you are standing, actually, if you change your angle a little, you're going to see different colors still. So during an oil spill, that matters too. So again, depending on this distance in here, and if you do the geometry correctly, using the angle of incidence, theta, which is the same angle as this one, by the way, And whether or not, because now this is the difference in path when it comes to the two, okay, delta, okay? And that delta depends on this T in here, okay? And this is the same angle theta. Depending on your angle, you're gonna see constructive or destructive interference again, depending on where you are, depending if there is a phase shift or not, because if this one comes in here, it might flip, depending on the index of refraction between the top and the bottom. If there is water actually in here, too, that is going to have all kinds of weird things in here happening, because the index of refraction of the oil, for example, is different than that of the water. And from that, you're going to have whether or not there is a phase shift for the wave that goes from this surface to here or not, okay? So again, that is what the essence of the colors are coming. It's coming from the fact that you have, of course, the thickness also in here too. So this is, no, that's thickness only the top layer. Doesn't matter. So the point being in here is that the interference in this case, what you see as colors, it is white light coming from the sun, which is a combination of all of the frequencies coming through. Because of destructive interference, some waves will be missing, some frequencies will be missing in the pattern, and you will be starting seeing colors from the same white light that arrives because of the fact that that is a known, that's basically how this phenomenon can be interpreted, okay? In terms of problems, again, the focus is going to be on 3 equations really. This one is one of them, actually 4 equations, I should say, the dark fringes and the bright fringes, and also the expression for the intensity. That is very important. And third, and the fourth equation is that of the position of the wave, position with respect to the from the center, which is given by this relationship. Y in general is equal to the tangent. Remember, we're going to take the tangent to be very small, the tangent approximation. Let me find where that expression is, because I know we wrote it several times. Here, this expression, okay, it's going to be coming handy. Okay, trying to find Y. In terms of lab also, that is a very important expression too. So those are the four things that are going to be needed for the homework, for the problem session on Wednesday. Okay, I'm going to stop sharing the screen. Again, there is no lab today this afternoon, but there will be a big lab coming next week. I will post the instructions hopefully this afternoon or tomorrow, with and maybe you guys can start on your lab too soon. Okay, thank you.